In class, we were working on this problem where we were analyzing the graph y equals the product of the sine function and the cosine function. And a number of students had some continuing questions relating to finding where various functions were positive and negative. So I wanted to illustrate how this works. And I'm going to do this a couple different ways. So we always want to start by remembering that when doing sine analysis, if we can factor it, it really helps. So for example, here as I'm looking at the sine and the cosine multiplied together, I can think about my function y equals sine x cosine x equals 0. We can find out where it crosses the axis by looking where each factor separately goes to 0. So for example, we could ask, well, where is the sine function by itself equals 0, and where is the cosine function by itself equals 0? And once I get it down to the basic trigonometric function, I can be thinking about this in the context of the unit circle. And so if I want to know where is the unit circle making the sine function 0, we remember that the sine function gives us the y value, and the cosine function gives us the x coordinate. So the y function, the y coordinate is 0 in two locations. And so those two locations are when my input x equals 0 or x equals pi. But it's also every 2 pi multiple, because if I go around the circle, I return back where I am. So not only is it when x equals 0, but it's every 2 pi. So we write every 2 pi k, where k is an integer, so plus or minus 1, plus or minus 2, and on and on. On the other side, x equals pi, well, it could be at negative pi or 3 pi. And so here I get every odd pi. So I get x equals pi plus 2 pi k. Again, k is all those integers. And so when I look at the full list, I get x equals 0, plus or minus pi, that's when I'm on the left, plus or minus 2 pi, that's back on the right, and this continues on forever. The cosine function is the x-coordinate, and so the x-coordinate equals 0 at the top and the bottom. And so when I think about where these are, this is at pi over 2 and at minus pi over 2. And again, every time I go around a full circle, I return to where I am. So my solutions for the cosine are x equals pi over 2 plus 2 pi k, because every full loop around the circle, I'm back where I started. And I'm at the bottom whenever x equals negative pi over 2 plus 2 pi k. And so if I thought about, well, what does this list create? This creates the list x equals pi over 2 and minus pi over 2. And then it gives me plus or minus 3 pi over 2, plus or minus 5 pi over 2, and on forever. And so these are the locations of all the spots where my y function is equal to 0. So if I want to know where is my function positive or negative, I use those points and do a sine analysis. So I just list where all those points are. So here's 0 at pi over 2, at minus pi over 2, at pi, at minus pi, at 3 pi over 2, at minus 3 pi over 2, and this would go on forever. And so these are the locations where my function equals 0. And now I want to think, well, okay, when is it positive and negative? To answer that question, again, I want to think about the unit circle. And so I've got my 4 quadrants. I've got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And in each quadrant I can decide, is the sine positive or negative, and is the cosine positive or negative. And so if I remember that the cosine is always the x-coordinate, cosine, and the sine is always the y-coordinate, then in each quadrant I can identify that the coordinates are either positive or negative, 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 or both positive. And I can now determine the product is going to be either positive or negative. So if I think about each little interval as being one of the quadrants, so for example, between 0 and pi over 2, I'm in quadrant 1. And so in quadrant 1, sine and cosine are both positive. So when I multiply them, I get a positive term. When I'm between negative pi over 2 and 0, I'm in the 4th quadrant. Negative pi over 2 to 0, I'm in the 4th quadrant. And so the cosine is positive, the sine is negative, and the product in the 4th quadrant is I get a negative value. And so as I go around the unit circle, I'm simply rotating through the 4 quadrants. And so I'm negative, positive. In the 2nd quadrant, I'm negative again. 3rd quadrant, positive, because both sine and cosine are negative. Back to the 4th quadrant. And so we see that we're just alternating among those different systems. Now that we found the signs of the function y, which is sine x, cosine x, the next step is to find the signs of the first derivative. So let's find the derivative. Notice that I need to use the product rule. I'm finding the product of sine and cosine. So when I take the derivative, so y prime is going to be the derivative of the first, cosine of x, times the second, leave it alone. So that means we have cosine squared. And then we add sine of x, because we leave the first alone. Then we take the derivative of the second, which is times negative sine of x. What that gives me is that my derivative is cosine squared minus sine squared. At this point I have 2 ways I can proceed. I could either factor this, in which case I get cosine of x plus sine of x times the cosine of x minus sine of x, because we have a difference of squares. Or I could take advantage of the fact that this derivative happens to be a double angle formula, the cosine of 2x. And I'll come back to that double angle formula in a bit. In class we did this factored approach, and so I want to continue on with that and show you how we would finish that problem. And hopefully it'll make a little more sense this time. So we want to know when the derivative equals 0. And again, just like for our original function, there are 2 pieces. Either the cosine of x plus the sine of x equals 0, which leads us to our first possibility, cosine of x plus sine of x equals 0. Or we could have from our second factor that the cosine of x minus the sine of x might equal 0. And this is the advantage of having a factored formula equals 0, because the product of 2 numbers can equal 0 only if at least one of the factors equals 0. So now I have to think about what this means, and this is the part that I think is the trickiest. I need to think about it in the context of the unit circle. So let me draw a unit circle for each problem. And let's think now what this means. Now x in the original problem refers to the independent variable. But on the unit circle, the cosine is the x-coordinate and the sine is the y-coordinate. So what this says about the unit circle is that x plus y equals 0. X plus y equals 0. And if I solve for y, that tells me y equals negative x. So on my unit circle, if I were to draw the y equals negative x graph, y equals negative x, there are 2 points on the unit circle where the y-coordinate is exactly opposite the x-coordinate. And if I consider what that is, the x-coordinate and the y-coordinate being the same means I have an isosceles right triangle, which tells me I have to be at the 45-degree angle. And so if I think about where I am on the unit circle, this first angle on the top left, quadrant 2, happens to be 1, 2, 3 45-degree angles, or 3/4 pi, 3 pi over 4. And if I go the other direction, I go exactly 1, and so this is negative pi over 4. In a similar way, if I think about the second factor, cosine x is the x-coordinate, sine x is the y-coordinate, and so I'm thinking about where the x minus the y equals 0. If I solve for y, I get y equals x. So the second factor is if I were to draw with the unit circle the line y equals x, there are 2 points on the unit circle where the x-coordinate and the y-coordinate are the same. And again, I'm at a isosceles right triangle, which again, I'm at the 45-degree angle. And so this first angle in the first quadrant is pi over 4, and in the third quadrant I'm at, well, there's 2 ways of getting there. I could go around in the positive direction, 1, 2, 3, 4, 5. So I might think of this as 5 pi over 4, but I could have gone in the negative direction, so an alternate might be negative 3 pi over 4. So that's how I get the basic angles of where each of the factors equals 0. Now that I know where this first derivative equals 0, we can make a number line. So I meant to be black. So we can make a number line. And we'll label each of the points where I'm possibly equals 0. So we are at pi over 4, 3 pi over 4, 5 pi over 4, and so we're going to be every odd pi over 4. So minus pi over 4. So these are all the places where I'm 0. And as I want to try to think about the sign in each of these subintervals, I'm going to be thinking about the products. And there's actually a way of doing it geometrically that might be a little harder. So the easiest way is probably to just pick values and determine the pattern. So for example, if I think about this interval between negative pi over 4 and pi over 4, the angle 0 is inside that interval. So here I am at the angle 0 on each of my pieces. And so if I plug in the angle 0, I'm going to get cosine is 1, the sine is 0. So the first factor is 1, and the second factor is 1. And when I multiply those, I get a positive term. The second interval, from pi over 4 to 3 pi over 4, again, the angle pi over 2, the 90-degree angle, is in that interval. So that's another example of a point that's easy to find. This time the cosine is 0 and the sine is 1. So the first factor is 1, the second factor is -1, and so we switch sign. And so I switch sign. And as I go around, I can identify each of the four 90-degree angles corresponds to points inside each of these intervals, and we happen to alternate sign as we go. And so now we have the signs for the first derivative. Now earlier I had pointed out that the derivative could have been rewritten using the double angle formula as the cosine of 2x. So now it's possible to think about finding my interpretation using this representation of cosine of 2x. I want to illustrate how that works. So if I want to know where y prime equals 0, I'm looking at where is the cosine of 2x equals 0. And the cosine, we've emphasized this a few times already, is the x-coordinate on the unit circle. And so if I think about the cosine equals 0, it's at the top and the bottom. And so at the top here I'm at pi over 2, and at the bottom I'm at negative pi over 2. And the difference that we have to keep in mind is that it's not the cosine of x, but it's the cosine of 2x. And so I'm going to have to think about my angle 2x equals pi over 2, or 2x equals negative pi over 2. So if I divide each of those by 2 in order to find my x, I get x equals pi over 4, or x equals negative pi over 4. Now normally I repeat every 2 pi, but I have to think about that in the language of my double angle. So my additional ones, 2x could have been pi over 2 plus multiples of 2 pi, 2 pi k. And when I divide by 2, I get x equals pi over 4. But instead of every 2 pi, it's every pi. And so for this first one, I would get pi over 4 plus pi, which happens to be 5 pi over 4. I would also get 5 plus another 4 is 9 pi over 4. If I add another 4 pi over 4, I get 13 pi over 4. And if I go to the second system, I'm going to get x equals negative pi over 4 plus pi times k, which gives me negative pi over 4. If I add 4 pi, so I get 3 pi over 4, 7 pi over 4, 11 pi over 4, and so on. And so I get the same positions that I had for the previous example. So when if I were to go and do my sign analysis for y prime, I would need to include every odd pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, and so on as I go around. If I want to think about my sign analysis, let me finish this negative 3 pi over 4. As I think about my sign analysis, if I think about a particular interval, negative pi over 4 to pi over 4, if I were to double that, I'd be from negative pi over 2 to pi over 2, So on the unit circle, that's where my cosine happens to be positive. If I were to think about this next interval, pi over 4 to 3 pi over 4, if I double that, because that's what this double angle formula does, I go from pi over 2 to 3 pi over 2. And so on the unit circle, I'm from pi over 2 to 3 pi over 2. Now my cosine is negative. And once I realize the pattern, I can determine the sines for each of the subintervals. So this is how you can use the double angle formula to figure out where my function is going to be positive and negative. Alright, finally to finish the problem we need the second derivative. So y double prime, let's see what we need to do. Turns out if I use the double angle formula, the cosine of 2x happens to be easy to calculate as derivative. The derivative of cosine is negative sine, so negative sine of 2x, and then the chain rule says I have to multiply by the derivative of what's inside, so I get negative 2 sine of 2x. If I use the original formula that I had before with the cosine squared minus the sine squared, I would need to use the chain rule with the power. So this is cosine squared. So the alternate approach is to say, okay, it's 2 times the cosine of x to the first power times the derivative of cosine. So times sine of x. And then we add. Okay, this time we have negative sine squared, we take a derivative, so we get negative 2 sine of x to the first power times the derivative of sine of x, so times cosine of x. And notice that these are actually, what did I miss? Oh, my mistake. The cosine's derivative is not sine. I lost a negative sign. So it's a negative sign. So I actually have the same formula twice, and so my derivative is negative 4 sine of x times cosine of x. Notice if you were to do the double angle formula for sine, sine of 2x is 2 sine x cosine x. I would recover the same formula. Well, we've already done this. We found all the sines of sine x times cosine of x, and now we're just taking negative 4 times that, and I can quickly get my sines by just taking the same intervals and changing all of the signs. Once we have all of the sine analysis complete, there is one more step, and that step is the interpretation step. So, to illustrate, I need to be sure that I say what my answer is. For example, y is positive on, and once I say on, then I'm going to start listing the intervals where it's positive. So let's see, we get the interval from 0 to pi over 2. I get the interval from pi to 3 pi over 2. And I'm going to start a pattern. 2 pi to 5 pi over 2, 3 pi to 7 pi over 2, and so on forever. And so that's where I'm positive. Of course, we also have the intervals on the negative side, so we think, well, is there a way of generalizing this pattern? Notice that I'm always starting at an integer of pi and then going up by an increase of pi over 2. So the generalization to be able to do this is to say that we start at an integer multiple of pi and we go to that same location plus pi over 2. And that describes each of the intervals as long as I say for k, it could be 0 plus or minus 1 plus or minus 2 and on. So now we have a pattern, and we've now described all of the intervals. We can do the same thing for where the function is negative. And we can get a similar formula. We realize that y is negative in many intervals. And notice that now the right endpoint is always an integer multiple of pi, and we're going to the left. And so we describe that as the right endpoint is k times pi, and it's k pi minus pi over 2 for the left endpoint. To answer where the function is increasing, we need to look at the derivative. So we say, well, where is the derivative positive? And I get these intervals, and this is starting to look a little trickier, but notice what's always in between. So here I have pi in between, I have 2 pi in between, and so it's always pi minus a quarter to pi plus a quarter. Which we can write as pi times k minus pi over 4 to pi k plus pi over 4, where k is again any integer. Then we can say where the function is decreasing by finding the intervals where it's negative. And the formula is a little trickier, and that's because it's not pi that's in between, but it's these odd half pi's, so pi over 2, 3 pi over 2. There is a way to write it in the language of those pi over 2's. I find it easier to think about where pi is, and so then I have to go pi over 4 to get the left endpoint, or 3 pi over 4 to get the right endpoint. And so that's what I've written. Well, concavity, I'm not going to write down concavity. It's exactly the opposite of how we would have written our function being positive or negative. So the way we write our intervals is the same. And I'm concave up on intervals where I'm positive in the second derivative. And I'm concave down for y, where the second derivative is negative. Finally, an important point. Notice that when I'm talking about increasing and decreasing, I'm looking at the first derivative, but I'm talking about the original function. Alright, well that's how we do this problem. And yes, it is complicated, it takes time, but the basic concepts are fairly straightforward. Good luck.